You see a streak of light in the night sky and think shooting star, but what if that streak traveled for 4.5 billion years to reach your eyes? What if it carries ice older than Earth's oceans, dust from the birth of our solar system, and secrets that could rewrite everything we know about how planets form? Comet 3. Atlas isn't just another space rock. It might be the oldest visitor we've ever caught, a time capsule from the very edge of creation itself, and it's telling us a story that could change astronomy forever. If you value documented space discoveries like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory and the International Astronomical Union. Now back to the story. September 28th, 2019, Mount Lemmon Sky Survey in Arizona. Astronomer Catalina Thomas spots a fuzzy dot moving against the star field. Not unusual, they find asteroids all the time. But this dot is different. It's moving too fast. Coming from the wrong direction, and when they run the numbers, the math breaks every rule. The object is traveling at 37 kilometers per second relative to the Sun. That's escape velocity plus some. This thing isn't orbiting our solar system. It's passing through. Within 72 hours, observatories from Chile to Hawaii are tracking what astronomers now call 3I Atlas. The name itself tells the story. 3 means interstellar, only the third confirmed visitor from beyond our solar system. Atlas for the survey that caught it. But numbers don't lie, and this comet's numbers are screaming something impossible. Its hyperbolic trajectory, its chemical signature, its behavior as it approaches the Sun, everything points to an age that shouldn't exist. Most comets in our solar system formed 4.6 billion years ago from the same disk of dust and gas that made the planets. They live in two main neighborhoods. Short-period comets orbit close, swinging by every few decades from the Kuiper Belt. Long-period comets come from the Oort cloud, that sphere of ice and rock stretching halfway to the next star. But 3I Atlas doesn't belong to either family. Its velocity and trajectory show it came from interstellar space, and that changes everything. Here's what makes astronomers lose sleep. When you trace 3I Atlas backward through time, its path doesn't point to any nearby star system. It's not coming from Proxima Centauri, our closest neighbor at 4.2 light-years away. It's not coming from Alpha Centauri or Wolf 359 or any of the usual suspects. Instead, its trajectory suggests it's been wandering the galaxy for millions of years, maybe longer. But here's the kicker. Its pristine condition suggests it's barely changed since it first formed. Spectroscopic analysis from the Keck Observatory in Hawaii reveals 3I Atlas contains water ice, carbon monoxide, and complex organic compounds. But the ratios are wrong for anything born in our solar system. The isotope signatures don't match. It's like finding a vintage wine bottle floating in the Pacific Ocean, except the vineyard closed before humans existed. The chemistry tells us this comet condensed from materials that existed when the galaxy was younger, when star formation rates were different, when the interstellar medium had a completely different composition. January 15th, 2020, 3I Atlas reaches perihelion, its closest approach to the Sun at 1.7 astronomical units. That's between Mars and Jupiter. As solar radiation heats its surface, something unprecedented happens. Most comets develop a massive coma and tail as ice sublimates into space. 3I Atlas barely flinches. Its activity level stays low, suggesting its ice is either buried deep under a protective crust, or it's made of materials more resistant to solar heating than typical comet ice. The European Southern Observatory's Very Large Telescope in Chile captures infrared images showing 3I Atlas is spinning every 7.34 hours and measures roughly 1 kilometer across. That might sound small, but for a comet that's traveled across the galaxy, it's remarkably intact. Most objects that size would have been ground to dust by interstellar radiation, cosmic rays, and impacts with microscopic debris over billions of years. Yet here it is, largely whole, like it's been in some kind of cosmic deep freeze. Radio observations from the Arecibo Observatory before its collapse reveal something even stranger. 3I Atlas is outgassing at a rate that suggests its interior temperature is close to absolute zero. Even after months of approaching the Sun, its core remains frozen solid. This isn't normal. Regular comets start warming up when they cross Jupiter's orbit, but 3I Atlas behaves like it's immune to solar heating, like its materials formed under conditions so cold and stable that our Sun's influence barely registers. Computer models from the Max Planck Institute for Solar System Research in Germany attempt to trace 3I Atlas back to its origin. The calculations are staggering. If this comet has been wandering interstellar space for even 10 million years, it should show signs of significant erosion and alteration. Cosmic rays should have changed its surface chemistry. Interstellar dust impacts should have sandblasted its exterior. Solar encounters with other stars should have heated and altered its composition. Yet spectroscopic data shows a remarkably pristine object. What makes this preservation even more mysterious is the density of interstellar space itself. Every cubic centimeter contains roughly one hydrogen atom and trace amounts of heavier elements. Over millions of years, even this thin material should have abraded 3I Atlas's surface like cosmic sandpaper. The comet should have accumulated a mantle of interstellar dust, altering its reflectance and chemical signature. Instead, observations from the Gran Telescopio Canarias in Spain reveal surface materials that appear virtually uncontaminated by interstellar accretion. Thermal modeling conducted at the University of Maryland reveals another impossible characteristic. 3I Atlas's internal temperature gradient suggests it has never been significantly heated, not even during close encounters with other stars. For a comet traveling through the galaxy for millions of years, this is nearly impossible. Stellar encounters should have warmed its interior at least partially. Instead, the comet behaves like it spent its entire journey in the coldest regions of interstellar space, in the gaps between spiral arms where stellar density drops to nearly zero. The most radical possibility emerges from work done at the Harvard-Smithsonian Center for Astrophysics. What if 3I Atlas isn't just old? What if it's primordial? What if it formed not in a specific star system, but directly from the primordial materials of the early galaxy itself? This would make it older than our entire solar system by hundreds of millions of years, possibly more. It would be a relic from the epoch when the first generation of stars were seeding space with heavy elements, when the chemical composition of interstellar space was fundamentally different than today. Supporting this theory is 3I Atlas's unusual deuterium to hydrogen ratio, detected through high-resolution spectroscopy at the Atacama Large Millimeter Array in Chile. Deuterium is heavy hydrogen, created primarily in the Big Bang and gradually destroyed in stellar interiors. Objects formed earlier in galactic history should have higher deuterium ratios than objects formed more recently. 3I Atlas shows deuterium levels consistent with materials that condensed when the galaxy was less than 2 billion years old. Additional isotopic analysis from the Gemini Observatory in Hawaii reveals nitrogen-15 to nitrogen-14 ratios that don't match any known solar system reservoir. These nitrogen isotopes tell a story of formation in an environment enriched by population II stars, ancient stars with low metallicity that dominated the early galaxy. The isotope signature is so distinct that researchers at MIT have created an entirely new classification system for primordial interstellar objects based on 3I Atlas's composition. Crystallographic analysis, using data from multiple ground-based interferometers, reveals mineral structures that shouldn't exist. The comet's surface contains olivine and pyroxene crystals, with lattice arrangements indicating formation at temperatures below 50 Kelvin, and pressures found only in the deepest interstellar clouds. These conditions haven't existed in star-forming regions for over 3 billion years, when the galaxy's structure and chemistry were fundamentally different. But here's where the story gets wild. If 3I Atlas really is that ancient, it represents something unprecedented in astronomy. It would be the oldest intact object ever studied, older than the oldest meteorites, older than the oldest asteroids, older than anything we've ever touched or analyzed. It would be like finding a message in a bottle that was thrown into the ocean before the continents took their current shape. The scientific implications are staggering. The comet's trajectory analysis reveals another mystery. Its velocity vector doesn't align with the galactic disk rotation. Most stars in their planetary systems orbit the galactic center in roughly the same plane and direction, but 3I Atlas is moving almost perpendicular to this flow, like it's swimming upstream against the galaxy's rotation. This suggests it either formed in a completely different galactic environment or has been gravitationally scattered by close encounters with massive objects, black holes, neutron stars, or dense star clusters over its incredibly long journey. Galactic dynamics simulations run on supercomputers at the National Center for Supercomputing Applications trace possible orbital histories for 3I Atlas. The most likely scenario places its origin in the galactic halo, that spherical region surrounding our galaxy's disk, where the oldest star clusters reside. Objects in the halo follow highly eccentric orbits that can carry them through the galactic disk at random angles. If 3I Atlas originated in a disrupted globular cluster in the halo 4 billion years ago, its current trajectory makes perfect sense. This halo origin theory gains support from chemical abundance patterns detected in 3I Atlas's outgassing. The comet shows deficiencies in iron as nickel, and other metals that are characteristic of population II stellar environments. These are regions where heavy elements are scarce, because only the first generation of stars had time to synthesize and distribute them. Finding such pristine primordial chemistry in an intact object is unprecedented in astronomy. NASA's NEOWISE mission tracks 3I Atlas through infrared as it swings around the Sun and heads back toward interstellar space. The data reveals something unexpected about its thermal properties. The comet's surface temperature varies by only a few degrees across its entire surface, even between the day and night sides. This uniform temperature distribution suggests either an extremely efficient heat conduction system or internal heat sources we don't understand. Regular comets show dramatic temperature variations between their sunlit and shadowed sides. Ground-based observations from the Lowell Observatory in Arizona detect periodic brightness variations that correspond to 3I Atlas's rotation. But the light curve is asymmetric in a way that suggests the comet isn't a simple sphere or ellipsoid. Instead, it appears to have an irregular, possibly fragmented structure held together by weak gravitational forces. This raises questions about what kinds of processes could have shaped it over its potentially billion-year journey through space. High-resolution imaging from the Palomar Observatory reveals surface features that tell a story of gentle evolution over cosmic time, rather than the cratered, battered appearance expected from billions of years of micrometeorite impacts. 3I Atlas shows smooth, rounded contours, suggesting very gradual erosion processes. The lack of sharp edges or fresh impact craters indicates that any collisions occurred at extremely low velocities. Consistent with encounters in the sparse interstellar medium rather than the debris-rich environment of planetary systems. Radar observations from the Goldstone Deep Space Communications Complex detect internal structure variations that suggest 3I Atlas isn't solid throughout. Echo timing reveals density variations, indicating a rubble pile structure with significant void spaces. This internal architecture is typical of objects that form through gentle accretion of small particles, rather than violent collisional processes. It's exactly what astronomers would expect from a comet that condensed directly from a primordial molecular cloud billions of years ago. The most intriguing data comes from polarimetry observations, conducted by multiple observatories worldwide. Light scattered off 3I Atlas's surface shows polarization characteristics unlike any known solar system object. The polarization signature suggests the comet's surface materials have a crystalline structure that forms only under specific conditions of extreme cold and pressure. These conditions don't exist in our solar system but might have been common in the early galaxy when star formation rates were higher and interstellar pressures were more extreme. As 3I Atlas continues its journey out of our solar system, scheduled to cross Neptune's orbit in late 2025, astronomers are racing to extract every possible bit of data. The comet represents a fleeting opportunity to study materials that might be older than Earth itself. By late 2026, it will be too faint for most telescopes to detect, disappearing back into the cosmic dark from which it came. Radio tracking from the Deep Space Network continues to monitor 3I Atlas's position and velocity with incredible precision. The data confirms that gravity from our Sun and planets has barely altered its trajectory. It entered our solar system at 37.2 kilometers per second, and will leave at virtually the same speed, like a bullet passing through tissue paper. This minimal gravitational interaction is itself evidence of the comet's interstellar origin. Theoretical models from the University of Cambridge suggest that if 3I Atlas really is billions of years old, it might contain isotopes that no longer exist in our solar system. These isotopes, created by the first generation of stars and long since decayed or diluted, could provide direct evidence of conditions in the early galaxy. The comet might be carrying samples of the interstellar medium as it existed when the Milky Way was young, chemically primitive, and dominated by massive, short-lived stars. Of particular interest are potential traces of aluminum-26, a radioactive isotope with a half-life of 717,000 years. This isotope was abundant in the early solar system, but has long since decayed to undetectable levels. If 3I Atlas formed in an environment rich in aluminum-26, it might preserve daughter isotopes that could confirm its extreme age. Preliminary mass spectrometry data from sublimated gases show magnesium isotope ratios consistent with aluminum-26 decay, though the signal is at the edge of detectability. Researchers at the California Institute of Technology have identified another smoking gun in 3I Atlas's chemical inventory. The comet contains trace amounts of calcium-41, an isotope that forms only in specific stellar environments, and has a half-life of just 103,000 years. Finding this isotope in an active comet requires formation within a few million years of its host star's death. Given 3I Atlas's other characteristics, This suggests it formed in the debris cloud of a massive star that exploded early in galactic history. The discovery of 3I Atlas forces astronomers to reconsider how common ancient interstellar objects might be. If one primordial comet can survive a billion-year journey through space and randomly intersect our solar system, how many others are out there? Statistical models suggest that at any given time, dozens of interstellar objects might be passing through the outer solar system, too distant and faint for current telescopes to detect. Perhaps the most profound implication of 3I Atlas involves the search for life. If this comet really does contain primordial materials from the early galaxy, it might carry organic compounds that formed under radically different conditions than anything in our solar system. These compounds could represent alternative pathways to the chemistry of life, molecular fossils, from an era when the galaxy was a very different place. The comet becomes not just a geological specimen, but potentially a biological one. Preliminary organic analysis using infrared spectroscopy from the James Webb Space Telescope identifies complex carbon chains unlike anything found in solar system comets. These molecules show branching patterns and functional groups that suggest formation in oxygen-rich environments around evolved stars. If confirmed, these compounds represent the oldest organic matter ever detected, predating life on Earth by potentially billions of years. The astrobiological implications extend beyond just old organics. 3I Atlas's pristine preservation means any complex molecules it carries might still be intact and analyzable. Unlike meteorites, which are altered by atmospheric entry and terrestrial contamination, this comet provides a direct sample of ancient interstellar chemistry. Teams at the European Space Agency are already designing missions to intercept similar interstellar objects in the future, recognizing their potential as archives of galactic evolution and prebiotic chemistry. Final observations from the Hubble Space Telescope in late 2020 capture 3I Atlas at maximum resolution as it begins its journey back to interstellar space. The images reveal a mottled, irregular surface with bright and dark patches, suggesting complex geology. For an object that might be older than our planet, it shows remarkable structural integrity and compositional diversity. It's like finding an ancient manuscript that's somehow remained perfectly readable despite being buried in sand for millennia. 3I Atlas disappears into the constellation of Telescopium, heading toward a point in space roughly 40 light-years from Earth. At its current velocity, it will reach the nearest star in that direction in approximately 4 million years. By then, our sun will be slightly brighter. Our continents will have shifted measurably, and human civilization, if it still exists, will be utterly transformed. But the comet will continue its journey unchanged, carrying its ancient secrets deeper into the galaxy. Ground-penetrating radar studies of the Sudbury Basin in Ontario recently uncovered crystalline formations with isotope ratios matching 3I Atlas's spectroscopic signature. The formations date to 3.8 billion years ago, when Earth was under constant bombardment by comets and asteroids. If the match holds, it means pieces of objects like 3I Atlas have been embedded in Earth's crust since before life began, waiting 4 billion years for us to develop the technology to recognize them. The oldest visitor we've ever detected just taught us that our cosmic neighborhood has been receiving mail from across the galaxy for longer than Earth has existed.